Thank you very much for the introduction. And thanks in general to the organizers for inviting me. That's a pleasure to be there today with you. I'm going to talk about a domain in which, together with my colleagues, we've been working for now more than a decade, and that we may call developmental machine learning. And I'm going to explain you or give you illustrations of dimension of this work, which is, if we want to summarize it in a sentence, it's about machines that learn a bit like children, and that can be used to help children learn better. Okay, let's begin by a comment on the recent advances in machine learning, and in particular in deep reinforcement learning, which is machines who learn how to act, how to decide sequences of actions to solve problems. And as you all know, there has been a number of very impressive progress that have been done by many teams in the world. One of them, which is quite paradigmatic, is AlphaGo, where deep reinforcement learning algorithms learn to play the game of Go at a level which is surpassing the world champion at the game of Go, which is something that probably 7-8 years ago many researchers would have thought it would have taken much longer. So that's extremely impressive. And there is a lot happening into the deep neural network machinery in those applications. The neural networks play many games against itself. In the latest version, it does not even use examples of games from humans. However, if we look at this summary of the research, as it is actually done many times in the media, we are actually missing some important aspect of the whole picture, why it's actually working. There is actually one very key actor in this process who is helping the computer to win, and this is the engineer. And the engineer is doing several things which are pretty key in the current success of AlphaGo, for example. So one kind of thing is that the engineer is programming in a few specific biases to the games. One of them, which is pretty important, is, for example, the rules of the game, which is typically, for example, what actions are possible and not possible. It's a game about moving those white and black blocks. It's not a game about, for example, winning by taking a big piece of wood and crushing the adversary. This is not an option to the machine. This is an option to a child who actually discovers how to play the game of Go, and the most difficult for a child is to understand the rules of the game of Go, even for an adult, by the way. But actually, even more importantly, what the engineer is doing is that she is programming an external reward, which means that the way those deep reinforcement learning work is that they are basically trying to optimize a number, a scalar number, which is called a reward, and it has to maximize it, and it's basically the number of points. So in the game of Go, it's 0 or 1, which is the win. In a video game, it's the number of points. But in all those applications, then the engineer needs to really literally write a piece of code, which is often not very trivial, to basically decide when the game is won or lost and the number of points. And for example, in the case of Go or in the case of video games, the piece of code necessary to program the reward is actually not trivial. It's not something that, for example, you could ask a high school programmer to do. It's more complicated than that. So that's an important part, and here if you want to have the AlphaGo, for example, switch to the game of chess or switch to the game of checkers, which is way more easy, actually you need the engineer to reprogram those external rewards. So it's not quite autonomous. It contrasts very strongly with the way children are learning. So first of all, when we look at children learning, there is something extremely striking, is the fact that they don't learn a single skill, like the game of Go, or solving certain particular kinds of mathematics, but they learn a wide diversity of skills. And actually very few of them become world champion at the game of Go. And becoming world champion at the game of Go is not something that's really like the extraordinary intelligence of children. Their extraordinary intelligence is the fact that they can adapt to many different environments, and they can learn many diverse skills, moving around, grasping objects, learning language, running bicycles, playing basic tunes with the guitar. This is what makes them really extraordinary learners. And they don't do that in a single step. They do that in a progressive manner. They begin by learning simple things. For example, they don't begin by learning on 2 feet. First, they learn to follow objects with their eyes. They learn to control their head, moving their neck. They learn to go from the belly to the back. They learn to sit, etc. It goes in a developmental sequence, from simple to more complex. And then one question one may ask is, what's the role of this sequence? Is this something that's actually slowing down the whole process, or is this something that is actually enabling to learn so complicated things? And so one thing that one must have in mind also when we look at human learning, child learning, and actually we compare, for example, to the way AlphaGo is processing, is that human learning is facing extremely severe limits of resources, of time, of energy, and of compute. Human beings are physical organisms, and the way to learn is by making physical experiments in the physical world, including interacting with social peers, and this literally takes time and energy. Which means they do not have the time, for example, to collect billions of examples of movements to learn how to grasp an object or how to move. They collect a lot, but not billions. And there are so many tasks. So for each of them, they have really limited resources to learn. And so probably this developmental structure is something that is maybe helping them. This is a hypothesis that we are studying, helping them to solve this problem of learning many things under these severe limits of time, energy, and compute. This is very different, for example, from the approach that people take to solve the game of Go. In the game of Go, the assumption is that compute is infinite, or close to infinite, if you want, and the question that engineers try to solve is, okay, how can we leverage this huge amount of compute to solve this peculiar predefined game? Okay, so this is very different. Children, it's about learning many skills and having severe limits of time and energy. And so basically studying those mechanisms, modeling them, is part of this field, developmental machine learning. It's also developmental robotics. I'll explain why we use the word robotics. We're not really doing robotics, but we use a lot of robots. I'll explain that in a few minutes. So first of all, one dimension of what we do is about developing algorithmic models to understand better the human. So the human, the child is learning as a complex system, and we cannot only understand, we cannot understand fully what it's doing only by observing, making verbal theories like in neuroscience psychology. We also need to have operational models of what they do. And then from those models, we try to transfer that to AI and to see to what extent it can enable some machines to have aspects of the capacities of child learning. And then there are a number of application fields. One of them is educational technologies, where we leverage some of the fundamental principles we've been understanding through modeling to try to help children learn better. And then there are other application fields, like, for example, automated discovery of chemicals or physics. I don't know if I will have time today to speak about that. Let's see. Okay. So now, the way we organize our research is by basically trying to understand what are the forces that are going to guide, to constrain, to bias embodied organisms like children to actually acquire relatively diverse sets of skills in the real world. And among those families that are biasing learning, that are constraining learning, that are making it possible to learn in the physical world, so one family is, for example, studying the role of embodiment, the role of morphology. If you look, for example, at the problem of learning how to walk, there is one way to learn about this problem, which is the control theory point of view, which is, okay, yeah, there is some robots that come from the mechanical engineering department. Whatever is morphology, okay, it gets into the control theory lab, and now the question is, how can we design a controller that's going to be able to decide every millisecond the optimal motor command to maximize forward speed while minimizing energy and avoiding to fall down. There is another approach to working, which is, okay, before thinking about the controller, maybe let's think about the morphology. Maybe designing a particular morphology may help in the control problem. And this is what people, for example, like Tad McGee, who is the guy on the video here, who is actually coming from aeronautics, where in aeronautics it's pretty standard to, like when you try to have planes fly, before thinking about the controllers, you think about aerodynamics. It's been not obvious at all in robotics for many years, and it's still not obvious at all in many areas of machine learning and robotics. So this guy basically tried to reproduce the geometry of human legs, some aspects of the geometry of human legs, the distribution of mass, for example, and then he played with mechanical toys like this one, showing that if you have actually the right morphology, the right distribution of mass, the right elastic properties, then you can actually have this mechanical structure work forever on a treadmill and actually adapt to small perturbations without a controller, without a single controller, without an energy supply. Here the energy supply is just the gravity, and there is nothing else, no computation at all. And so when you look at that, you understand that now the control problem is very, very different from, for example, trying to control a humanoid robot like the P3 humanoid robot from Honda, which you may have seen on TV. Here, learning to work is actually learning to perturbate a dynamical system which is already very organized, very structured. So that's a very different problem. And so we've been trying, for example, to leverage this kind of approach in a little bit more complex robots, robots with a torso, for example, to understand how they can face external perturbations, and also how they can handle physical interactions with humans. And so, as you can see here, for example, this robot. When you take it by the hand, and you don't actually even need to pull it toward yourself, it's going to follow you. And this is actually something we did not initially design for. It's something we discovered at a science festival. Basically at this science festival, at some point there were little girls like this one, who were taking the hands of the robot, and the robot was following. And the guy who actually made the robot and programmed the controller, it was Olivier Lee. He was next to me, and I asked him, oh, I didn't know you programmed in this new feature. And he said, I didn't. And so we were quite astonished, and we tried to understand. And actually, it's pretty simple. This robot has a vertebral column, which, by the way, we designed inspired by the way biomechanicists who study human walking have identified a few important degrees of freedom in the vertebral column. And so it has a specific geometry which allows certain kinds of deformations and not others. And also it has elastics a bit everywhere to enable physical compliance with external perturbation. And when you take actually the hands like this, it just moves the center of gravity of the robot a little bit forward. Okay? And there are also elastics in the end. And so there is a tension which is produced in the legs, and at some point it's released, and naturally the elastics go on like this. And actually, because the vertebral column can be also turned, and there is also tensions in this direction, it naturally follows the movement of the guy taking the hand. So here again, if you take the control theory problem, this might be a very difficult problem, because here you have not only a complex system, but you have a human with unpredictable actions in front of you. But if you take the mechanical engineering approach, where physics take a big role, then you might simplify the machine learning problem, or the control problem, even before talking of machine learning. So that's one family of forces that we study. There are other families of studies that of forces that we studied. Another family is cognitive biases. So for example, there is one thing that children are extremely good at is learning language, learning new words extremely fast from very few examples. And this is a bit of a conundrum from a mathematical point of view, because, like, for example, if I show you this and I say to you it's a wabadoo, or imagine you show that to a machine. He sees that image, and the machine, I tell him it's a wabadoo. Like, from a mathematical point of view, first of all, it's going to make statistics over the pixels. And even with one image, it's not going to be able to do a lot of statistics. He will need a few of images. I will try to see which features of the pixels kind of correlate with the word wabadoo. And I guess it will take a lot of images if you consider things like, for example, shape, color. You might have even things like sizes or objects with the blue things on it. So there is an infinite number of hypotheses you can make. So how do children guess relevantly the meaning. It's because simply they have biases where they prefer some hypotheses over others. And the kind of preferences they have is in terms of affordances. When they see, for example, a new word in a new situation, they try to build hypotheses of the meaning in terms of what they can do with this object. Which means that if they've already explored the world, they've probably played with that a lot. They've discovered that if they open it, there is liquid that can go out of it, and they can put it in their mouth, and they've seen people taking it and putting it in the mouth to drink. And so the thing they will probably, the first hypothesis they will make is that Wabadu is something you can drink in. That's probably the first hypothesis they will make, if they have played with that before. Another kind of important family for guiding machine learning system is obviously, and that's related to language, the social context. The fact that children are learning with peers who have had a lot of learning experiences so far and who can transmit through cultural interaction this knowledge. But today I'm going to focus actually on another family of biases, which is related to the autonomy of learning in children, which is related to what psychologists call intrinsic motivation and what in everyday language we may call curiosity. So rather than long words, here is what I'm talking about. Here you see a child. He's in the living room of his house, and he's not, if you might think about the evolutionary fitness of this guy, the evolutionary fitness is defined in terms of how good he will reproduce when he gets old. So probably, like thinking from kind of an optimal control point of view, maybe he should first make sure he gets old and not die. And maybe the optimal thing to do when he's in this kind of environment is just wait on his and sit and wait that when he's angry the parents come to feed him. But it's not at all what he's doing. He's exploring many objects, he's touching them, he's throwing them, he's seeing the sounds they produce, and there is no parents around to give them an objective, to give them a task. He is deciding or she is deciding by herself what to do, when to do it. And actually, when the parents may come in, they might actually try to prevent this little guy or this little girl to do some things, for example, putting the fingers in the plug, because this guy at some point will put his fingers in the plug. But then actually, if the parent is trying to be angry at the child by putting the finger in the plug, in general, the normal reaction of most of the children is to do it again. And it's very fun for them to do it again, because now what they're exploring is not the plug anymore, it's the reaction of the parents. So they spontaneously explore a lot. And it's actually extremely difficult to prevent them from exploring and self-generating their own goals. And I'm going to illustrate that by now showing you some videos that are of experiments that are happening in the lab of developmental psychologists who try to study the way children are learning. And actually what's interesting is that developmental psychologists, the classical paradigms that they are using for studying how children are learning are very similar to the most classical paradigms people are using to evaluate the performance of machine learning algorithms, especially deep reinforcement learning algorithms. The way they proceed is that they invent a task. In that particular case, you will see that's a task that's about using tool use. I'm going to explain that in a minute. They invent a task, a problem to solve. They try to explain it as clearly as they can to the child. And then they assess the intelligence or the learning capacities or the adaptability of the child as compared to their performance to these imposed external tasks. Okay, so let's see. So here, that's a task about tool use. Tool use is, by the way, often used by developmental psychologists as some kind of marker of the capacity of complex planning. And basically, the way the experimenter is proceeding here is that she is putting in the little tube on the middle a colorful toy and tries to select the toy to be as desirable as possible to the child. And then the tube is transparent and everything else is made on purpose to be as dull as possible, so that the child gets, from the experimental point of view, its attention attracted to the car, and it's kind of trying to define as clearly as possible that the goal is about getting the car in the tube, okay? And you just saw one run of the episode, and maybe you think actually the child succeeded very well. So let's now see the same video, but until the end. No, sorry, it's the following slide. So the mother is very happy, the experimenter also, so there is some kind of external reward. But then the child puts the car back into the tube. So you say, okay, what's happening? So let's see other children. So this is actually a study we made with developmental psychologists where we try to deconstruct those paradigms. This is a little girl. She seems to be very concentrated, to be working hard. What did happen? So, okay, so the car went out. She didn't care. And not only she didn't care, I don't know if you heard, when the car went out, she said, oh no. So actually, from her point of view, she failed. And what was she doing? If you heard, she was making choo-choo. So she was actually playing the little train. So she was doing something completely different. So from the point of view of the experimenter, the developmental psychologist, success. She passed the test. Is this really a success? She was doing something else. She discovered how to get the car out. But is this really a success, the one that the experimenter wanted to have? And here is the best video. That's my preferred. This one does not care at all about the car and the tube. And actually he discovered that the little pieces of wood in front of it can be used as a chalk to make drawing on the other piece of wood. So this guy is literally a genius, because he finds out there is an affordance, a tool use of those things that the experimenter didn't even think about. But he fails the test. So typically what we observe here is that even if the experimenter is trying to design an environment to make the goal obvious, the children, they are always doing something else. They do whatever they want, they self-generate their own goals, and this is the way they learn. And we see actually with the girl here that's actually generating her own goal is actually a way to find out, to discover how to solve complex problems like the car. Maybe later on, now she wants to get the car, and now she knows how to get the car. And so by the way, that's also a very interesting metaphor for understanding the limits of current paradigms to study, for example, the behavior of deep reinforcement learning algorithms, where you give to those algorithms a task and you only measure their performance. Like 99% of the paper in the deep reinforcement learning literature are about comparing those algorithms with respect to their performance of the final task, but not really evaluating qualitatively what's happening in the strategies they develop to get those points. And we see here that actually very intelligent things can happen even if the task is not solved, and very stupid things can happen even if the task is solved. Okay, so now let's look at more precisely those mechanisms where the children spontaneously explore. And this is actually a topic that has been a lot discussed by psychologists right from the 50s in the last century under the terminology of intrinsic motivation. And they have generated hypotheses like maybe in the child there are neural circuits who lead them to be intrinsically interested by situations where there is high uncertainty, high novelty, high surprise. They spoke about cognitive dissonance, optimal challenge. So they used a lot of verbal theories like this. But unfortunately, there is very little operational mathematical models that were developed until relatively recently. We're actually a network of labs in the world, a few computational labs like mine, but a few neuroscience labs, for example, like the one of Jacqueline Gottlieb, or developmental psychologist lab like the one of Celeste Kidd, have been really now beginning at studying operationally what's happening into the, in the head of those children when they spontaneously explore. And the conceptual approach to do that has been to basically conceptualize the child as a sense-making organism. So it's basically the child as a little scientist who is, when he's not angry and thirsty, is basically free to explore, and then when he is exploring, he's basically motivated to build good predictive models of the world, or good models that enable to control the world. And this happens through experimentations and observation, through a relatively standard machinery of learning, and in particular that can be modeled by machine learning. But then the question is, how do they organize their experiments? Why do they decide to experiment this thing or this thing in this order and with this particular timing? And so basically what we've been trying to understand is what are the meta architecture, the meta mechanisms that enable them to decide those experiments. And typically these architectures are about tracking the quality of the learning of the normal model with things like novelty, uncertainty, and other things. I will discuss that again in a few minutes. And then to have a measure of interestingness of the experiments, which will produce some form of internal rewards, what we call intrinsic rewards, that is going to be used by an action selection system, an experimental selection system, into the head of the system to decide for the next experiment. And what's also interesting to understand is that there are several kinds of experiments that can be made. So two important families of experiments are, on one hand, prediction experiments. So a prediction experiment is one where, for example, in a given context, those two children, they have the idea, okay, let's mix chemicals of this color and this color, and we predict that it may give, for example, the color black, but we don't really know. Let's try. And so they try, and then they observe the real color, and based on the observation, they update their model. But there is another kind of very important experiment, which are goal achievement experiments. So here it's not like those children are doing like, let's try to put these little pieces of wood and let's see what it gives. No, no, they imagine a goal. For example, let's build a tower. And okay, given what we know right now, let's try to achieve that goal. And so they will try out those things, reusing their current world model, and probably they will make mistakes on the way, and those mistakes are actually going to be to enable to improve the model. But the dynamics is a bit different. And so basically we try to experiment this approach by using robotic playgrounds of this type. So for example, you see on the left a robotic playground where we've been testing some algorithms for modeling spontaneous exploration, where the little guy in the middle is basically discovering his body, is discovering how certain parameters of movements produce certain kinds of effects on objects, such as movements, sounds, and basically this little guy is going to progressively discover that certain movements of its legs can push or grasp a few objects, and so other movements of his body. He has a simulated vocal tract that can produce sounds, enable actually to produce effects on this little social P on its right, who is actually pre-programmed to respond to the vocalization. And this guy is going to discover those affordances. And on the right, we have actually another robotic setup, which I'm going to describe in a few minutes, which is about discovering complex tool use. And the reason we are using robotic playgrounds is not so much that we are interested in the end to build very advanced robots and to do robotics. It's rather we use robots as important tools to investigate the mechanisms of learning in the real world under limited constraints of time, resources, and compute. Of course, we use a lot of simulations, like many labs in the world, because it's very practical to debug, to make simulation, to make statistics over the algorithms. But we also force us regularly to make experiments on those real robot platforms, because if we only work with simulated environment, it's very easy to, in a way, cheat. Like to allow ourselves, for example, millions of iterations of a learning system in a simulated world, which may actually be done in a few hours on a supercomputer. But in the end, we may not have learned a lot about the real mechanisms that are happening in the real world, because when we allow ourselves millions of steps, billions of steps, maybe the solutions we find out are very, very, very different from the one we need to learn from much less samples in the real world. So we need to find out what's happening in those real conditions. And there are a number of ingredients which we found are pretty important. So one first ingredient that is very, very important to enable efficient sensory motor learning in the real world is what's called dynamic movement primitives. Children, when they learn how to move, actually, they don't learn how to move by learning to send sequences of micro commands to their muscles every milliseconds and having a separate command to each of their muscles. Actually, their body is organized with what's called neuromuscular synergies, which are kind of relatively innate dynamical systems that connect multiple muscles through low-level neural networks, which are pretty close in the body to the muscles, and who basically a bit like the dynamic walker that you see here. It's at the level of the coupling of the neural systems and the muscles. They already have some structures, and so it means that initially, actually, their brain not directly controls each muscle independently. It rather controls the parameters of those low-level dynamical systems who already have a lot of structures. And it's why, by the way, when you see very little children moving around in the beginning, their movement is not so unorganized as it might be, for example, as if you send random motor commands every 20 milliseconds in all the motors of a robot, it will produce very, very different movements. So that's something very, very important. And there is one particular tool that has been used a lot in the literature, and that's called dynamic movement primitives, that is modeling this kind of thing. There is another ingredient which is pretty important, which is the fact that not all learning happens at the same time. It's developmental, and one of the important things is that, for example, when you look at the time where infants begin to learn about object affordances, when they learn how to grasp objects, how to use tools, before that, they have been exposed immensely to the perceptual world. Before they actually begin to touch in complex ways objects, they have been exposed to a lot of images in many different contexts, which means that it's probably reasonable to think that at this point when they begin those complex sensory motor learning, they already have the concept of an object, or a primitive concept of an object. So it means that they don't start from the pixels to learn those skills. They start from higher level object-based, object-centered representations. Another ingredient that we've been using a lot is self-supervised learning of forward and inverse models. So basically learning of the correspondences between the motor parameters and the effect on those objects with what's called hindsight learning. So hindsight learning is basically when, for example, you have a machine or a human who's trying to push an object on the right, and he's trying to push the object on the right, and he fails, but the object goes on the left. Well, in hindsight, you can use that data to retrain yourself. Okay, if I want it to go on the left, now I have this data which enables to train my model. And the other thing is episodic memory, which is that in addition, or even sometimes in replacement of trying to learn a compact parametric representation that is summarizing many episodes of actions and outcomes, you can have an explicit memory memorizing all the explicit individual experiences and reuse that memory for fast retrieval and solving of problems who are very similar to the one you encountered in the past. And then the last family of mechanisms is how experiments are organized with time, and that's the curiosity part I'm going to talk to you about. So now the question is, what's an interesting learning experiment? So now this robot has those ingredients, those primitives, those perception of object, but how does it decide what's interesting to experiment? There are many ideas that have been proposed in the literature. I'm not going to review them, but they run from, for example, if you just look at the machine learning literature, from high uncertainty, surprise, free energy. But the one I'm going to detail a bit to you today is one which we found very useful in the context of having robots that learn autonomously models of the world in the real world, and in an environment that are rich enough such that there are a lot of either distractors or tasks that are too complicated for them to learn, but as well as other tasks which are too easy. And this family of mechanism is basically called the absolute learning progress hypothesis. And the fundamental intuition is the following one. Imagine that there are several kind of experiments that the machine or the living organisms can make. Several goals, several kinds of goals, for example, you may consider. And imagine that the machine could play which of these activities or goals for a little while, and we would have a graph showing the evolution of its errors in predicting or control over time. And so the basic idea is that if we would know in advance those curves, the most useful way to explore is basically by avoiding to explore those where there is no progress that can be done, either because it's too easy or too complicated. Maybe it's too complicated because, for example, the phenomenon depends on variables that are completely not observed and not controllable. And maybe first focus on the one where there is maximal learning progress, and when it reaches a plateau, switch to the other kind of activity. And if you do that, it's actually a very good strategy to learn very fast, to be good in average over the learnable activities in the world. The problem is that in the real world, activities don't come pre-segmented in various kinds of activities, and we don't know in advance those learning curves. So it means we have to have an approach to discover that at the same time. And so let me describe one possible approach to do that. And so first of all, like a little bit more detail on the framework we use to approach that. So here we, for example, consider that we have an organism, a robot, for example, that it can produce parameterized actions, parameterized action policies, starting from a state S. And those policies can be, for example, dynamic motion primitives, or they can be recurrent neural network. Here we don't really care. In experiments we do later on, I will show it dynamic motion primitives. And then when those policies are run, produces a sequence of states and micro actions, a trajectory, and from this trajectory there are what we call behavioral descriptors of the full trajectory, which are computed. They could be pre-programmed, they could be learned, and they could be things like the mean speed of one object along the trajectory, or the result of a classifier deciding whether an event has occurred on the trajectory, or maybe it could be, for example, the embedding of a recurrent neural network that has been trying to summarize the whole trajectory in a fixed vector. And basically, this behavioral descriptor space is going to be used in several ways. So one first thing what can learn from this framework is the forward model, which is basically the relation, given a state and the parameters of the policy, what are the behavioral descriptors of the full trajectory that are going to happen. And another thing that you can learn is the inverse model, which is given a state and the final set vector of descriptors, what's the parameters of the policy that are going to minimize the difference with those target descriptors. And basically, you can use the idea of learning progress in several ways. You can use it, for example, by choosing which parameters of policies and which state to explore to maximize the learning progress in predicting the quality of the forward model. So that's what we call prediction progress. But you can also focus on learning progress on the inverse model, which is basically you imagine a goal, which is a set of values for those descriptors, and then you launch a system for trying to achieve those goals, and you basically, the progress here is competence progress, the speed at which you improve over your skills to reach those goals. And then how to do that more precisely? So we have this space of descriptors, which we are going to use as a space of goals. So we will sample goals in that space, so it's typically continuous and high dimensional. And so that space of goal is going to be progressively split into subspaces by some algorithm, so I won't enter into the details of that, but the basic idea of this algorithm is that it's basically trying to maximize the difference of learnability among those subparts. And then each of the little regions of the space, of the goal space, the system is going to monitor the evolution of its errors in control, what we call competence, and it's going to compute the absolute value of the derivative, which we call the absolute learning progress. And then it's going to use this absolute learning progress value to achieve goals in different regions as a utility function, which is given to a bounded algorithm to select in what subregions of the goal space it is useful to sample goals in order to maximize globally the quality of an inverse model here. Okay? So that's basically a mechanism that's going to be used to generate progressively a curriculum of learning for learning an inverse model here. And by the way, the exact same approach can be used to train, I'm going to give you shortly an example, a goal condition deep reinforcement learning algorithm, where here we sample the goal with this mechanism. Okay, so there was a first experiment I wanted to show you, but I will skip it. I will directly to go to a more interesting experiment to go a bit faster in the talk. So let's see an example of an experiment where we've been using this approach. So that's an experiment where we have a robot like the humanoid torso on the top, and actually we have a little farm of those robots which enables us to do several experiments in parallel to have more data. And basically those robots are equipped with dynamic motion primitives which enable to control one of the two arms, so the other one is not used in that space, and which basically it means that your action is a vector of 32 dimension that is producing a dynamic movement of the arm. And then there is a high dimensional behavioral descriptor space, which is basically a space describing the trajectory in space as well as the trajectory in sound and in color of multiple objects in the environment, including the hand. So let's see a bit more in video how this environment is looking like. And so initially, the robot is actually, in that case, already have a perceptual module where it's able to track the position, color, and sound of all the objects. So it's leveraging an object-based representation from the start. And each of those goal space is in general between 10 and 20 dimensional to represent trajectories, target trajectories of those objects. And there are many objects around. There are objects like the hand, which is just one object like the other. There are objects like the two little joysticks in front of it. There are objects which are a bit farther, which cannot be controlled at all, but the robot doesn't know. And there are also objects you don't see here, which are objects which move by themselves and which are distractors. They cannot be controlled, they cannot be learned, but also the robot doesn't know initially. And so basically, initially, this robot will sample goals in all those subspaces and try to estimate the learning progress he makes in controlling them. And pretty quickly, we'll identify that the space in which it's making most learning progress is the one associated to the hand. And this is here some kind of internal representation of the learning progress in the hand. And it will begin by exploring more goals in that space, which is going as a side effect to improve the diversity of movements of the hand, which will make him discover that actually there are now two new spaces in which he can make learning progress, which is moving those two joysticks. But actually, one of them is especially interesting because quickly he discovers that it can move the other little white electric toy in front of it. The other one does not produce any special effect. So now, this white electric toy becomes an interesting space to generate goals, different movements, and he's focusing them. The bandit is now identifying that as a source of learning progress. And by doing this, it leads the robot actually to discover that now there is another source of learning progress, which is moving the ball around. Actually, this is a strategy he found, which we did not actually intend in the beginning, is actually hiding the ball from the object detection, so it's like the ball disappears completely. And actually the ball, when it moves around, depending on the position, it can trigger lights and sounds. So there is a whole chain of events that can happen. It's like a nested tool use. Like the robot basically in the end learns how to use its hands, to move the joystick, to move the electric toys, to move the ball, to produce particular light patterns. So here we see also a feature that's possible in this architecture, but it's not necessary for it to succeed, which is the ability for a human to show particular effects in the environment and to show some salience of on some particular things that can happen, and he might incentivize him to explore more certain things. And so what's interesting is that here, there is not an external problem who has provided to the system from the beginning. For example, there is not an engineer providing an external reward to move the ball forward. By the way, if we would have taken the vanilla reinforcement learning approach, where we want the robot to learn to move the ball forward, 1 centimeter 1 point, 10 centimeter 10 points, 0 centimeter 0 points, then it would not work. In the sense that we would have to wait millions of interactions before, by chance, the robot makes a movement that makes to move the ball, because in the vanilla reinforcement learning approach, when there is no reward and no gradients to compute on the reward, there is just random action selection, and random action selection here has a very low probability to get to move the ball. Whereas here, this robot, which is motivated by generating its own goals and generating its own curriculum over those objects, it discovers very quickly how to move that ball around, as well as a number of other things. So now a remark. So I said to you that in that particular case, the machine comes with a predefined perceptual space organized around representing the trajectory of objects, but it's also possible to have this kind of architecture. If one really wants to work with pixels, it's possible to have this approach. So if one wants really to work with pixels, what one can do is to use some tools like beta variational autoencoders, which are kinds of neural networks who tend to learn compressed representation of a scene, and such that the different dimensions of the embedding that are learned are in some way disentangled from each other, which means, like intuitively, like it may learn a representation where some different dimensions may correspond to features of one object and other dimensions to features of another object. And that's an interesting kind of machine to learn from pixels, because when we have this disentangled learned representation, then we can leverage the modularity of this representation to generate goals in this embedding, but not in the full embedding, in subspaces of the embedding, which will correspond to features of those objects. And so this is what we've been exploring with some of this architecture. it works relatively well in simulations, but it doesn't work very well in real-world robots. Those machines, like the variational autoencoders, are still far from being efficient in the real world. Okay, so now, in the last few minutes I have, I'm going to shift through a number of, more quickly a number of things, but just to give you a sense of the perspectives. So first of all, let's come back a little while to models of child developmental data, because those experiments I presented to you, they are about spaces, sensory motor spaces, which are not exactly like the spaces of, they are not explicitly modeling spaces of children. So we've been looking more closely at trying to account for particular developmental data by modeling, for example, what's happening into vocal exploration. So we've been using a physical model of the vocal tract. So when I say physical, it's simulated, like a simulation of the physics of the vocal tract. Trying to understand what's happening when we use those models of spontaneous exploration to learn inverse models on vocal development. And basically what we've been observed is that we see the emergence of developmental phases which are very much like the developmental phases of vocalization we see in children, like for example the first phase where it's about learning phonation. Actually most movements of the vocal tract don't produce sounds at all, followed by a stage where they are actually producing sounds like R, which are alternation of vowels, and finally canonical babbling like ba, 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 ma, ma, ma. And also, we've also enabled those models to take advantage potentially of an existing repertoire of sounds in the environment which is already structured and which can be chosen to be imitated. And here the bandit also decides whether to imitate or not the sounds of the environment based on the learning progress. And what we've seen is that initially the system is not so much interested by imitating the external sounds because no progress is made because it has not the basic control building blocks for doing that. They are too complicated. But at some points of self-exploration, he acquires those skills and now he makes progress and he shifts towards imitating. And this shift from babbling not influenced by the social environment to babbling influenced by the environment is exactly the shift we observed at the stage of canonical babbling in human infants. So that's actually a model that has enabled to provide an explanation to a developmental progression that was so far unexplained. We've been using also those models in contexts where, for example, we combine the use of a simulated vocal tract with a full body that can interact with objects, with a simulated vocal social peer in front of the machine. And then we've shown that actually in that context, the learner with this kind of architecture can learn on one hand to manipulate objects, to discover that some objects can be used as tools to move other objects, but also we discover that actually the vocal tract movement can produce certain sounds that can be used to modulate the behavior of the social peer, to influence the social peer, so that, for example, the social peer will take an object which is too far away to put it in front of the learner and to play with it. So in a way, through this approach, we see the discovery of the linguistic function of speech. Speech, producing speech wave as tool use for influencing social peers. And this is completely emergent in this kind of systems, tool use and the linguistic function of speech, and this is the natural dynamics of those systems. Quickly, I told you that those approaches can be used to train other kinds of machine. Like here it was about having a machine that's autonomous in self-engineering its own goals and learning forward and inverse models, but it can be used more traditionally, for example, to automate the curriculum learning of more traditional machines, like, for example, LSTM, so natural language processing tasks. This was done, for example, in a 2017 paper by Grace, Belmar, and her colleagues. More recently, for example, we've been studying their efficiency in guiding, in generating the curriculum of deep reinforcement learning algorithms. So here, actually, the idea was, okay, we are not anymore in a multitask setting. We are a setting where there is a single task, which is about learning to run as fast as possible over obstacles in a simulated world like this one. But the problem is that we have a black box learner, so that's a DPRL algorithm, but it could be any DPRL algorithm. That's a black box body, like the body is something that's generated also with various properties, and we don't know those properties of the bodies. And then we have an ability to generate procedurally environments with many, many shapes and obstacles. And we want actually these black box learners to take him as far as possible, given his unknown capacities that we need to discover, and to basically enable him to be very good at the skill over a wide diversity of obstacles. And so, for example, here we have a way to procedurally generate obstacles in spaces that can have more than 10 dimensions, and it's very difficult by the end to imagine a curriculum of what's simple or what's impossible for the machine. It's very difficult a priori. And also, if you sample randomly this space of environments, a big majority of them are just either trivial or infeasible. So it's also very inefficient. And so basically, we can show that we can use this automated curriculum learning approach. And in the end, we have those systems who learn very robustly to work in, over obstacles who are constantly changing. And exactly what we just did here with black box learner, and I will conclude by this, we have recently, actually in the last, not so recently, in the last 3-4 years, applied it to human learners, which is exactly reusing the same idea of trying to model the performance of the learner over diverse kinds of tasks or diverse kinds of environments and automate the curriculum learning. And we've done that, for example, with testing this approach to try to personalize sequences of exercises for children. In that case, it's in the domain of mathematics in primary schools. And so the idea is exactly the same. So we have a teacher algorithm, which is basically the one I've been talking for several slides, who is basically trying in sequence to recommend exercises. So here there is a slight difference. It's not imposing the exercise to the child, it's leaving some choice to the child. It's a recommendation. It's important because children, they have a complex motivational system, and having them choose something is important in the learning progress. So we recommend them a few well-selected exercises, and they do it. And depending on the result, the algorithm goes on like this. And another little shift of the idea that I presented to you before is that because also human learners, we don't want to waste their time, and they have not thousands of exercises they can make in the classroom, we kind of hot start the system with a little bit of prior knowledge from a pedagogical expert. And this prior knowledge is instilled in the form of a graph of activity, a graph of exercises, which is basically the pedagogical experts make big categories of exercises, and in them, inside each of them, it makes kind of big, rough organization of difficulty, and he puts a few edges on the transition that may be possible in this graph. But still, many possible paths are possible in this graph. And basically, we begin by a bandit, which is only considering a few families of exercises at the root of the graph. And basically, we are going to progressively deform the bandits based on if you want, the basis of the bandit, the number of arms, if you want. We are going to change that dynamically, depending also on the performances of the children, and to choose inside the bandit based on the learning progress. And basically, we've been trying to test this algorithm in large-scale experiments over actually more than 1,000 7 and 8 years old children, and we compare that with actually an algorithm which was that's kind of an oracle, because it was made by the pedagogical expert to try to personalize depending on various kinds of errors made by the children. And we were able to show that not only this algorithm is able to actually get the children higher than the pedagogical expert, but also we evaluated the impact of motivation on the children. And we found that for a subclass of the children, the one who are self-regulated, the one who likes, for example, to choose their clothes in the morning, they are much more motivated when they play with the automated algorithm than when they play with a software where the sequence is made by a pedagogical expert. I will stop there. Thank you.
Okay, so thank you for this presentation. Questions?
Sorry, my question may be quite naive because I'm not at all in that field, but it's the following. I mean, it's said that for very young children, particularly, there is a fast reconstruction of the brain, of the neural circuits. And so my question is whether, to what level this impacts your analysis on one hand, and secondly, if there is any, what is also, I mean, if pure software approaches model or to reproduce the behavior of the children. Up to what level is it applicable, or shouldn't we consider, I mean, models that really take into account this reconstruction?
I'm sorry, I didn't understand. What's the phenomena of children you are referring to?
Again, I'm not a specialist. Just what I read is that the brain is rapidly evolving. I mean, the neural circuits. I mean,
okay.
This is it.
Yeah. So yeah, that's an important part. So actually, the brain is rapidly evolving from multiple perspectives. So first of all, there are new synapses, new neurons that are created, but also the way those neurons are functioning is evolving. And not only in the brain, actually it's in the full body. For example, there is myelination, which is a process which is not fully finished when children are born, and which basically control the spatio-temporal resolution of the signals that go through the neurons. And that's what's basically called maturation. And aspect of those mechanisms can be actually studied from the perspective of mechanisms where complexity of the neural system, but also of the system for communication, is growing in complexity. And this is something we have actually studied in other models I did not present to you here, where we've been at the same time studying the opportunities of that, the fact that like it's not only the body growing, but the neural capacities in their power are growing, both computationally in their speed of processing information. And in some, like if for example, we made models on that, in some cases it's facilitating the learning. In some other cases, it's actually making it more difficult because, for example, these growths make that new degrees of freedom kind of become possible at some point because like you have a finer control over the muscles. And so, for example, there are redundancies that appear in the system and that might perturbate the learned model. And so actually for addressing that, we've used also this curriculum learning approach based on absolute learning progress. And that's useful because it enables a learner in a growing body to discover that there are skills that before it mastered very well, but because his body has changed, now they are not so well mastered. And so it needs to re-explore them. And that's why, also I didn't explain that, it's important to look at the absolute learning progress. So it's not like only increase in performances, which is interesting, but also decrease in performances. Like a statistically significant decrease in performances means there is something interesting happening.
Hi, thank you for the very nice talk. My question was about the goals. You mentioned both experiments that had like fixed goals, and you tried to tackle the pixel point of view where we have like a version autoencoder. The question is, how is it? Do you have any ideas on how to tackle real children goals, which seems to be evolving and getting more complex as they go? For instance, when you start driving a car, it's really hard, and you have very like, you know, multidimensional sub-goals, and then it just becomes drives from there to here.
Okay. So for comments here, goals are never fixed. What is sometimes fixed is the representation in which they are formulated. So in the robots I showed you, goals are not fixed, but the representation space is pre-given, but it's pretty large, and inside it only a small part is relevant, and the system needs to discover which part. So next, your second question, yes, is a very fundamental question here, like beyond learning simple embeddings like with variational autoencoders, what's like the long-term interesting question is how to learn more abstract representation of goals, in a way how to model the capacity of the child to ask more and more complex questions over the environment. And so one of the approaches we are, for example, investigating right now in some other project is to leverage natural language to actually formulate new, more organized, complex questions. It's basically the idea that the child is going to learn elements of language, combinatorial language, by interacting with a social peer, and then leveraging this combinatorial structure to imagine new questions. Some of them may be stupid, some others may be very interesting, to ask kind of a bit more abstract, but it's yes, it's a very challenging perspective.